At the time of recording this video, it was yesterday that I released a video about the tensor product of vector spaces. And there were some questions in the comments about this formal product or free product of vector spaces that we used in order to eventually construct this tensor product of vector spaces. And so I thought I'd make another video because I think these videos are fun to make. And in fact, I think if you were to really ask me, I would rather make videos like this than all of the contest type videos. But I'll continue to do a variety of videos on the channel, hopefully doing more of these in the future. So we want to start off with a definition which will be related to this free product or formal product, but it's even a little bit more general. And we'll see how this definition can give rise to this free product. And it has to do with vector spaces defined with regards to sets. So let's say we're given any set S, the free vector space over R on the set S is the set of all finite formal sums of elements in S with coefficients in R. So there's a lot to parse out there, but I want to point out that we're forming a vector space over the real numbers, although you could do this with any field. And we'll parse these kind of things in this paragraph out via some examples, which I think will make it a little bit more clear. And we'll also sketch a proof that this in fact forms a vector space and show how it's related to the formal product, which we saw earlier. But before we get started, let's maybe point towards the question of why. Maybe this is not a super satisfying answer, but this is the answer that I have at the moment. And that would be this kind of object. And when I say this kind of object, this free vector space, or this like free group or free algebra, there are these free objects in all sorts of settings in mathematics. They play universal roles in order to form other objects. So in this case, the free vector space over a set plays a universal role to form other vector spaces. And that formation of other vector spaces is via quotients, as we saw in the last video. So in the last video, we formed V tensor W, although you could also form V direct sum W. Those are in some ways quotients or simplifications of this enormous free object. Okay, so let's look at some examples. So while we look at these examples, we're going to use the notion V of S to mean the free vector space on the set S. We could maybe put a subscript R here if we wanted to get really fancy with it, but we'll just leave it as V of S. So our first example will be with maybe the simplest set, and that will be the empty set. So what's the free vector space over the empty set? So that's going to be all finite formal sums of elements in S. So we would maybe write that like this. So if V is in the empty set, then V will be equal to the sum as I goes from 1 to n of A sub I times, maybe we'll say V sub I, where here A sub I comes from the real numbers. So those are the coefficients here. And then V sub I comes from our set, but our set is the empty set. But now we run into a problem here because the empty set clearly doesn't have any elements. So that makes this thing an empty sum. So let's write that down. This is an empty sum. But what's the value of an empty sum? Well, there's only one reasonable value for an empty sum, and that is the number 0. Just like there's only one reasonable value for an empty product, and that's the number 1. That's because 0 is the additive identity, while 1 is the multiplicative identity. So this equals 0. Now, this may seem like a problem because it looks like we've shown that every vector in this free vector space from the empty set is the 0 vector, but that's actually okay because there is a unique 0-dimensional vector space, which is just got the 0 vector in it. So let's see, we have a conclusion here that our free vector space on the empty set is really just equal to the singleton 0, which is the 0-dimensional vector space. So let's maybe move up one And we could say, well, what happens if instead of having the empty set, we have a singleton? So let's say S is maybe just made up of a single element X. Well, that means that if we take V in VS, then like we have here, V is going to be a finite formal sum of elements in S. So here the VI will be in S. But if VI is in S, then it can only be equal to one element. So that means that we have V equals A times X, where A is a real number and this X is whatever the element of S is. Okay, so in fact, this has infinitely many elements because we can scale A any way we want to. And in fact, this is also one-dimensional. And we can summarize this by saying that V of S in this case is really just the same thing as the one-dimensional vector space given by the real numbers. We might in fact call this the real numbers times X. That would be like a one-dimensional span of this vector X or this element X from the set S. So let's maybe do another quick example or two, and then we'll prove that this indeed makes a vector space. So for our third example, we're going to look at the set S, which has n elements, and we'll name those n elements x1 through xn, although they really could be named anything. Okay, so now let's say if V is in VS, so it's a finite formal sum of guys like this. So that means that V equals the sum as I goes from 1 to n of AI x sub I. So in other words, it looks something like this. A1 x1 plus A2 x2 plus dot 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 AN xn, where our AIs run over the real numbers like this. And now there are a few questions here, like what's the zero vector? Well, the zero vector will be 0 times x1 plus 0 times x2 all the way up to 0 times xn. In other words, it's this empty sum over elements from this set, or it's just the one where we're weighting all of the elements from the set with the number 0. And now I'd like to point out that this is clearly n-dimensional. So in this case, we could say that VS is isomorphic to Rn, where the isomorphism is given by xi being sent to ei, which would just be the column vector where we have all zeros except for a 1 in the ith component. So that's like a standard basis, if you will. So let's look at one more standard example before we look at kind of a crazy example, which really highlights how this allows us to create some pretty crazy vector spaces. Okay, so the last example that we'll look at that is standard will be if we take the set S to be equal to all powers of x. So let's say 1x, x squared, x cubed, x to the fourth, and so on and so forth. But that means if we have a V in VS, then that means that V equals A0 plus A1x plus A2x squared all the way up to AN x to the n. So we know it's a finite sum. So since it's a finite sum, there is a largest power of x in that sum. And furthermore, we can just add in a bunch of zeros in the middle, so it looks like we've got all of the terms from A0 to AN, where in fact we need not have that. For example, we could have a vector, which I'll call W just to distinguish it, which is 3 plus 5x squared minus 7x to the 100. Which can be written obviously in this way if we include a bunch of zeros in there, like 0 times x to the 1, so on and so forth. Now, as we've been doing with these other cases, maybe we should write this as a familiar vector space, and that's not too hard here either. V of S is just the vector space of polynomials. So I would write that as R adjoin X, but you could also write that as maybe this fancy P. That's another standard notation for the vector space of polynomials. Okay, so the examples that we've seen so far really just produce well-known or commonly seen vector spaces by taking the free vector space on some set. Let's look at maybe a less well-known vector space produced from this construction. So now we're ready to really look at an example which will show us how this free vector space can be used to construct some really crazy things. And that is if we take S to be the real numbers. So let's look over here at our definition again, just so that we have a feel for what's going on. So a vector in V of S in this case, so let's start off with that. A vector in V of S will be a finite formal sum of elements in S with coefficients in R. Now this is a little bit tricky because elements of S are real numbers and our coefficients are also real numbers, but these are playing different roles here, so they cannot be combined. So let's look at an example of an element in V of S. Maybe we'll write it out in general, and then after writing out in general, we'll look at some cases. So here V would maybe have this form. So it would be the sum as I goes from 1 up to n, ai. Now I'm going to use a slightly different color here just to show that these guys are playing different roles. And here I'll maybe underline this in pink to just show that the pink role is being played by the elements from this set. Whereas the ones that are just standard in white chalk will be the coefficients. So this will be the sum as I goes from 1 to n, ai, and then I'll write vi here. And let's point out that ai is a real number, but then vi is also a real number because it's in the set. So let's point out that this is because our vector space is over the real numbers. In other words, the coefficients of the sums of our vector space come from the real numbers, or our scalar multiplication happens from elements of the real numbers. But this thing right here is because the set forming our free vector space is the real numbers as well. Another thing that's really important to point out here is that these two guys cannot be multiplied. So can't be multiplied. And that's because we've got this word formal sums, finite formal sums of elements in S with coefficients in R. Just like before, we were taking things like x1 and x2. And when you see things like x1 and x2 or x and x squared and x cubed, it's easy to look at those and see that they differ from the coefficients. But here it's a little bit trickier. There is a hack to make it look a little bit nicer, which we'll look at later. But I think it's nice to look at it in this confusing way first, just to really open your mind up to what's going on here. So now let's look at some examples of elements in this V of S, or this V of R in this case. So here are some examples, and I'll use my color coding here. So let's do 3 times 2 plus 5 times 3. So that's a finite formal linear combination of elements in R. So there are my coefficients, 3 and 5, and here are my elements from my set, 2 and 3. So 2 and 3 are seen as linearly independent vectors in this space. So since they're linearly independent, there's no way to add these nicely. Okay, so let's look at maybe another example, which is a little more unnerving. And that would be something like this. Let's take 7. So that means it has the coefficient 1 if I don't write anything down there. And then let's add that to 7 times the vector minus 1. So again, this does not simplify because this 7 and this minus 1 are seen to be linearly independent. That's again what I mean by these formal sums over here. These guys are totally different objects. Okay, so as we've sort of pointed out, this is really not great because it's super confusing how to write these things down. What's maybe a fix for this? I think maybe a good fix for this would be to subscript the basis vectors, so it doesn't really look like we're using the number 2 and the number 3 as basis vectors. So let's maybe write this as a little bit more understandable. So maybe we would say V equals the sum as I goes from 1 up to n of A sub I. And now we'll write V sub X sub I. So we're subscripting this vector V with X sub I. And here we have A sub I and X sub I are real numbers. So now some elements in this set will actually these exact elements in this set maybe take on a kind of a nicer form. So this would be 3v2 plus 5v3. And written like this, there's no really worry about trying to add those two things together because v2 and v3 look different. Now let's go over here, and this would be like v7 plus 7v minus 1. And again, v7 and v minus 1 have no reason to be related to each other, so there's no way that we would like really want to add those. So again, you can write it like this. It's a little bit less confusing, but what's really happening is that we're taking this finite formal sum over elements from our set S. So even though this is problematic in terms of notation, this is maybe more at the heart of what's going on with this construction. Okay, so now let's maybe look at a short proof. We won't look at all of the details that this does indeed form a vector space. Now we're going to do a short like hand wavy argument that for any set S, V of S, in other words, this free vector space defined on S is in fact a vector space. But this is really going to be not super satisfying because with any of these sort of universal or free constructions, often the way out of anything that's problematic is just to endow it with the correct structure. So anytime something looks like it will not work, we'll just redefine the operation so that it does work. Okay, so let's maybe get going here. So what is the zero element? Maybe that's our first question. And the zero vector here will just be the empty sum. So what do I mean by the empty sum? Well, that's the sum with no elements. Well, that's definitely a finite formal sum of elements in S. We're just not adding any of them together. And then I think you can check here that if V equals the sum as I goes from 1 to n of AI, VI, where AI is a real number and VI is in S, so again, an arbitrary element from V of S, it is pretty clear that 0 plus V is the same thing as V plus 0, which is the same thing as V. Okay, now that we've got this, we've actually kind of skipped a step, and that is how to define the addition in the first place. So let's maybe look at that real quick. And after we have addition defined, it's fairly easy to define everything else. So let's say that V equals the sum as I goes from 1 up to n of AI, VI, just like it was up here, where AI are real numbers and VI are elements from our set. And let's say W is another vector. So that's going to be the sum as I goes from 1 up to m of BI, WI. And now we want to look at the question of how to add V plus W. But how to add this can be described just by how to add two multiples of basis vectors and then extended linearly. So let's see maybe how we would do that. So we would say something like AIVI plus BIWI just stays as is. So it's not simplifiable if VI is equal to WI. So let's write that down. So not simplifiable if VI is not equal to WI. And that's because, again, we've got this finite formal sum, formal being the key word there. But if VI is equal to WI, we could write this as AI plus BI, where that addition is occurring in the real numbers, times VI. Let's maybe point out that this only works if VI is equal to WI. So that's the only time we get simplification. Okay, now that we've got this addition of basis vectors going on, well, we can easily extend that to addition of arbitrary vectors. And then from there, everything else about the status of this as a vector space follows pretty easily. Let's finish this off with a quick rundown of how this relates to our formal product, which was used to construct our tensor product of vector spaces. Now we're ready to finish this off with the relationship between the free vector space and V star W, where V and W are both vector spaces. Okay, so first off, you take VW as vector spaces, and then you form the set S. And the set S is all symbols of this form. So we've got V star W, little v, little w, where V comes from V and W comes from W. And here there are no relations between these symbols. So we better point that out. So no relations here. So even though they may seem like they should be the same, this star is a formal product. Nothing can move from one side of the star to the other, even if these guys have the same shape. And then from here, we would set capital V star W equal to V of S, or the free vector space defined on this set S. Okay, so let's maybe look at some examples here. So let's say that V equals W equals the 0 vector space. Okay, that means that S is equal to 0 star 0, right? So that's not 0, that is the element from V starred with the element from W. It's a single element. But that means that if you take the formal span of guys like this, you get a one-dimensional vector space. So in this case, I'll rewrite it as V star W. This will be one-dimensional. So now let's maybe look at another example. So let's take V to be equal to the 0 vector space, and then let's take W to be equal to just the real numbers. So in that case, we have our set S will be 0 star A, where A runs over all real numbers. And that's because for choices of elements in V, we only have 0. But for choices of elements in W, we've got all real numbers. So now if we were to form VS out of this, which is also V star R, or the 0 vector space starred with the real numbers, we get a hugely infinitely dimensional vector space. So this is infinite dimensional, but it's not only infinite dimensional, it's uncountable. And it's uncountable because every element like this from S is a basis vector. But look, the basis vectors are indexed by the real numbers, which themselves are uncountable. And I hope you guys found this interesting, and this patches some of the questions from the previous video. And that's a good place to stop.